Bond enthalpy is the enthalpy change required to break a particular bond in 1 mole of a gaseous molecule. We can see the bond enthalpies for carbon-carbon single, double, and triple bonds. You can see that the bond enthalpy increases as we have more bonds. It is increasingly difficult and takes more energy to break more bonds. Double more than triple, single, and triple more than double or single. But also, having more bonds, the bond length will decrease. For each bond, the atoms are going to be brought closer and closer together. So we go from 1.54 angstroms to 1.34 to 1.20 angstroms between the nuclei of the atoms. An angstrom, by the way, is 1/10 of a picometer. So increasing number of bonds between atoms, increasing bond enthalpy, energy required to break the bonds, and then a decreasing bond length. Now we can see that bond enthalpy is the amount of potential energy needed to break a bond. So let's consider a potential energy diagram versus the distance of separation between the nuclei of atoms. First, let's look at hydrogen. So, taking a look at hydrogen here, say the hydrogen atoms are far apart. So initially, they're not yet bonded together, nor are their s orbitals overlapping. This is not very stabilizing, so they're fairly high in potential energy, near zero, like they're in a vacuum. But as the atoms approach each other, they'll have s orbitals start overlapping. This is moderately stabilizing because electrons from each atom now can be attracted to the nuclei of the other atoms. So it's nice to have negative electrons on one atom being attracted to the positive nuclei of now both atoms. And so as we go in and the atoms get closer and closer together, there's a drop in potential energy. There is a stabilizing that occurs until some minimum well point here, where the atoms are most stable, being at this distance. This bond length is the minimum energy, is the bond length where there is the minimum amount of energy. Now, this amount of energy required to get us back to being gases, like in a vacuum, this amount of energy required to break the bonds is the bond enthalpy. Now, if those atoms approached each other even more, if they got even closer together, they would start increasing in energy rapidly. Because though it's nice to have the negative electrons get even closer to the positive nuclei, they're now become more significant negative repulsions between electrons and the positive repulsions between the nuclei of the atoms. The atoms will tend to have about this bond length because this is the most stable position to have this bond length. It's the lowest energy. Now, we can also now look at some other elements, like instead of just hydrogen, compared to nitrogen. Now, nitrogen has triple bonds. Having bonds between the atoms now, can go even lower in energy. The amount of energy required to break those bonds is even bigger than that of hydrogen, because having triple bonds is more stabilizing than having single bonds. But also, we can see that the bond distance of the nitrogen molecule is greater than the bond distance of the hydrogen molecule, as nitrogen atoms are much larger than hydrogen atoms. Nitrogen atoms have 2 shells filled instead of just 1 for hydrogen. So you can see here that the nitrogen had a greater bond distance and also greater bond enthalpy than that of hydrogen. Okay, so we mentioned that electrons will often, the bond distance will often be of this length of the minimal potential energy. But sometimes the molecule will absorb infrared light. And when it absorbs infrared light, it will go up in energy. And so now we have our bond lengths either being at this distance or at this distance. And so, in fact, you see that the bond length hops between this distance and this distance over and over again after hydrogen has absorbed infrared light. The molecule is vibrating. You can see a depiction of this here, whereas normally being of low energy, there's a very stable and typical bond length. Having absorbed infrared light, now there's a short, and then there's a long, and then there's a short, and then there's a long bond length. There's vibration of the bonds. Microwave radiation, if it is absorbed, it causes rotation of the atoms around the central atom. Now, you recall that if UV light or visible light is absorbed, electron transitions occur instead of vibrations or rotations. For example, an electron would hop up from n is equal to 1 to n is equal to 3, say. Okay. Now we'll be doing some calculations related to bond enthalpy. They're based around this idea that atoms are higher in enthalpy than molecules, because atoms, which are in their gaseous state, are not very stable compared to atoms which are bound to other atoms in molecules. So if you take some molecule and turn it into atoms, if you break bonds, that requires energy. So a certain amount of energy is required. That is the summation of the bond enthalpies of the bonds in the reactants. And then to form bonds again, in forming the molecule, that should be stabilizing going down in enthalpy. And that is equal to the negative of the bond enthalpy of the products, which you'll see here. Now, you can calculate the heats of reactions, the heat of turning reactants into products using Hess's law. You know that the bond enthalpy of the reactants here in this case is equal to the bond enthalpy of the products plus the plus the heat of the reaction. So heat of the reaction plus bond enthalpy is equal to the bond enthalpy of the reactants. And you can rearrange this to find the heat of the reaction by subtracting bond enthalpy of products from both sides. So the heat of the reaction is equal to bond enthalpy of reactants minus bond enthalpy of products. So you saw in this case that more energy was required to break the bonds of the reactants than was released in the formation of the bonds in the products. In that case, we saw that energy was absorbed. There was an increase in enthalpy going from reactants to products. And so that absorbing of energy by the reaction meant that it was exothermic. Okay, so more energy is required to break the bonds than is released when forming the bonds. So there's an increase in enthalpy. It's this is an endothermic reaction. Please correct that in the notes, endothermic reaction. So you can use this important equation. Heat of the reaction is equal to the summation of bond enthalpy of reactants minus summation of the bond enthalpy of products in solving problems like this one. Take this reaction. An N2 molecule reacts with 3 F2 molecules to give 2 NF3s. You can find the heat of the reaction by using the bond enthalpies of all the reactants. Heat of reaction is equal to the bond enthalpy of reactants minus the bond enthalpy of the products. Plug in and account for the number of bonds. Like for our reactants, we had 1 N triple bond. So 1 times the bond enthalpy of triple N triple bonds. Plus, there were 3 F single bonds. So 3 times the bond enthalpy of F single bonds. And then subtract now the bond enthalpy of the products. There were 6 NF bonds, so 6 times the bond enthalpy of NF bonds, and combine it all and you get the heat of the reaction is equal to negative 215 kilojoules per mole. In this case, less energy was required to break the bonds than was released in forming the bonds. There's overall stabilization. That is an exothermic reaction. Thanks for watching, guys.